The existing 1/0 THHN copper wire is adequate for the 175 amps breaker. According to NEC Table 310.15b16, 1/0 THHN can carry 170 amps in an underground raceway. It is generally not recommended to tap a circuit on the load side of a disconnect. The disconnect is intended to isolate the entire circuit, and tapping into it could create a safety hazard. The proper way to tap the circuit is on the line side of the disconnect. This will ensure that the tap is protected by the disconnect. Tap conductors must be sized according to the load they will be supplying. In this case, the tap conductors must be sized for the combined load of the two pumps and the water heater. Total load 11.9 amps plus 1.9 amps plus 3000 watts divided by 480 volts equals 20.4 amps. According to NEC Table 310.15b16, number 10 THHN copper wire can carry 25 amps in an underground raceway. Therefore, number 10 THHN copper wire would be suitable for the tap. The motor with the VFD should be protected using a VFD-rated disconnect and overload relay. The motor with the disconnect/starter should be protected using a magnetic-only circuit breaker or a fuse disconnect. The water heater should be protected using a 30 amps disconnect switch. Recommended circuit configuration 1. Tap into the line side of the 200 amps fuse disconnect using number 10 THHN copper wire. 2. Install a junction box at the tap point. 3. Run number 10 THHN copper wire from the junction box to each of the following components: motor with VFD, motor with disconnect/starter, water heater. 4. Install appropriate protection devices for each component as described above. When dealing with electrical installations, understanding the National Electrical Code, or NEC, is paramount. The NEC provides guidelines and standards to ensure electrical safety and proper functioning of electrical systems. Wire sizing is one of the most critical aspects of electrical work, as it directly impacts the safety and efficiency of the system. Selecting the correct wire size ensures that the conductors can handle the intended load without overheating, which can lead to insulation damage, fire hazards, and system failures. NEC Table 310.15b16 is a crucial resource for determining the ampacity of conductors based on their size, insulation type, and installation conditions. Ampacity refers to the maximum amount of current, measured in amps, that a conductor can carry continuously without exceeding its temperature rating. The table provides ampacity values for various conductor sizes, typically expressed in American wire gauge or AUG, for different insulation types such as THHN, THW, and XHHW. These insulation types have different temperature ratings, which affect their ampacity. Insulation conditions also play a significant role. For example, conductors installed in free air can dissipate heat more effectively than those installed in conduits or raceways, resulting in higher ampacity. Underground installations, as mentioned in the context, have different ampacity ratings compared to above-ground installations due to the heat dissipation characteristics of the surrounding soil. When selecting wire size, it is essential to consider not only the ampacity of the conductor but also the voltage drop. Voltage drop refers to the reduction in voltage along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce the brightness of lights, and decrease the efficiency of motors. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to know the conductor's length, current, and resistance. The resistance of a conductor depends on its material, size, and temperature. Larger conductors have low resistance, resulting in less voltage drop. Tapping into an existing circuit requires careful consideration to ensure that the existing circuit can handle the additional load. A tap is a connection made to an existing conductor to supply power to a new load. It is generally recommended to tap into the line side of a disconnect switch rather than the load side. The line side refers to the incoming power supply to the disconnect, while the load side refers to the outgoing power supply to the equipment being served. Tapping into the line side ensures that the new tap is protected by the disconnect switch. If a fault occurs in the tap, the disconnect switch will trip, isolating the entire circuit and preventing further damage or injury. Tapping into the load side, on the other hand, bypasses the disconnect switch, which can create a safety hazard. If a fault occurs in the equipment connected to the load side, the disconnect switch will not trip, potentially leading to a sustained fault current and increased risk of fire or electrical shock. The size of the tap conductors must be adequate to carry the load they will be supplying. The NEC requires that tap conductors have an ampacity equal to or greater than the non-continuous load plus 125% of the continuous load. Continuous load refers to a load that operates for 3 hours or more at a time. In the example provided, the tap conductors need to supply power to 2 pumps and a water heater. The total load is calculated by adding the current of the pumps and the water heater. The current of the water heater is calculated by dividing its power rating in watts by the voltage. In this case, the water heater is rated at 3000 watts and operates at 480 volts, so its current is 3000 watts divided by 480 volts, which equals 6.25 amps. The total load is then 11.9 amps plus 1.9 amps plus 6.25 amps, which equals 20.5 amps. According to NEC Table 310.15b16, number 10 THHN copper wire has an ampacity of 25 amps, which is greater than the calculated load of 20.5 amps. Therefore, number 10 THHN copper wire would be suitable for the tap conductors. In addition to wire sizing, proper protection devices are essential for ensuring the safety and reliability of electrical equipment. Motors and water heaters require specific protection devices to prevent damage from overloads, short circuits, and other faults. Motors, in particular, are susceptible to overloads, which occur when the motor draws more current than its rated capacity. Overloads can cause the motor to overheat, leading to insulation damage and premature failure. To protect motors from overloads, overload relays are commonly used. Overload relays are designed to trip and disconnect the motor from the power supply when an overload condition is detected. These relays can be thermal, magnetic, or electronic, and they are typically adjustable to match the motor's full load current. In addition to overload protection, motors also require short circuit protection. Short circuits occur when there is a low resistance path between 2 conductors, resulting in a high fault current. Short circuits can cause severe damage to the motor and other electrical equipment. To protect motors from short circuits, circuit breakers or fuses are used. Circuit breakers are electromechanical devices that trip and interrupt the circuit when a fault current is detected. Fuses are overcurrent protection devices that contain a fusible link that melts and opens the circuit when a fault current occurs. When using a VFD, or a variable frequency drive, to control a motor, it is essential to use a VFD-rated disconnect switch. VFD can generate harmonic currents that can interfere with the operation of standard disconnect switches. VFD-rated disconnect switches are designed to withstand these harmonic currents and provide reliable isolation of the motor. Water heaters also require overcurrent protection. The NEC requires that water heaters be protected by a circuit breaker or fuses size no larger than 125% of the water heater's rated current. In the example provided, the water heater has a power rating of 3000 watts and operates at 480 volts, so its rated current is 6.25 amps. 125% of 6.25 amps is 7.81 amps. Therefore, the water heater should be protected by a 15 amp circuit breaker or fuses. A disconnect switch should also be installed to provide a means of disconnecting the water heater from the power supply for maintenance or repair. A disconnect switch should be rated for the voltage and current of the water heater. In summary, when tapping into an existing circuit, it is essential to follow the guidelines and standards outlined in NEC. Proper wire sizing, tap location, and protection devices are crucial for ensuring the safety and reliability of the electrical system. Always consult with a qualified electrician to ensure that the installation is code compliant and meets the specific requirements of the application. Remember to always energize the circuit before working on it and to use appropriate personal protective equipment. Firstly, understand the existing circuit, determine the size of the existing conductors and the rating of the overcurrent protection device protecting the circuit. Secondly, calculate the total load of the new equipment that will be connected to the circuit. This includes the current draw of the pumps and the water heater. Thirdly, determine the appropriate size of the tap conductors based on the calculated load. The tap conductors must have an ampacity equal to or greater than the non-continuous load plus 125% of the continuous load. Fourthly, tap into the line side of the disconnect switch rather than the load side. This ensures that the new tap is protected by the disconnect switch. Fifthly, install appropriate protection devices for the new equipment. Motors should be protected by overload relays and circuit breakers or fuses. Water heaters should be protected by a circuit breaker or fuses and a disconnect switch. Sixthly, ensure that all connections are made properly and that the wiring is installed in accordance with the NEC. Use appropriate wire connectors and raceways to protect the conductors. Seventhly, test the installation after it is completed to ensure that it is working properly. Check the voltage and current at the new equipment to verify that they are within the specified limits. Eighthly, document the installation for future reference. This includes the size of the tap conductors, the rating of the protection devices, and the location of the tap point. Ninthly, always follow the NEC and local electrical codes. The NEC provides minimum safety standards for electrical installations. Local electrical codes may have additional requirements that must be followed. Tenthly, consult with a qualified electrician if you have any questions or concerns about the installation. A qualified electrician can help ensure that the installation is code compliant and safe. When working with electrical systems, safety is always the top priority. Firstly, always de-energize the circuit before working on it. Use a voltage tester to verify that the circuit is de-energized. Secondly, wear appropriate personal protective equipment, including safety glasses, gloves, and insulated shoes. Thirdly, use insulated tools to prevent electrical shock. Fourthly, never work on electrical systems in wet or damp conditions. Fifthly, be aware of your surroundings and avoid contact with grounded objects. Sixthly, if you are not comfortable working on electrical systems, hire a qualified electrician. An underground raceway, as referred to in the NEC, is a raceway installed underground. A raceway is a channel designed to hold and protect electrical wires and cables. Underground raceways are commonly used to run electrical conductors beneath the surface of the earth, providing protection from physical damage and environmental factors. There are several types of underground raceways, including rigid metal conduit, intermediate metal conduit, electrical metallic tubing, rigid polyvinyl chloride conduit, and reinforced thermosetting resin conduit. Each type of raceway has its own advantages and disadvantages, and the choice of raceway depends on the specific application and the requirements of the local electrical code. When installing underground raceways, it is important to follow the manufacturer's instructions and the requirements of the NEC. The NEC specifies the minimum burial depths for underground raceways depending on the type of raceway and the voltage of the conductors. The NEC also specifies the requirements for grounding and bonding underground raceways to ensure electrical safety. Underground raceways are commonly used to supply power to outdoor equipment, such as chillers, pumps, and lighting fixtures. They are also used to run electrical conductors between buildings or structures. The NEC provides specific requirements for the installation of underground conductors, including the type of installation required and the ampacity of the conductors. When installing underground conductors, it is important to consider the environmental conditions such as the soil type, moisture content, and temperature. These factors can affect the ampacity of the conductors and the lifespan of the raceway. In addition to electrical considerations, it is also important to consider the physical protection of underground raceways. The raceways should be installed in a location where they are not subject to physical damage from vehicles, equipment, or other sources. The raceway should also be protected from corrosion and other environmental factors. Regular inspection and maintenance of underground raceways are essential to ensure their continued performance and safety. The raceways should be inspected for signs of damage, corrosion, or other problems. Any necessary repairs should be made promptly to prevent further damage or safety hazards. In summary, underground raceways are an important component of electrical systems, providing a safe and reliable way to run electrical conductors beneath the surface of the Earth. Proper installation, maintenance, and inspection of underground raceways are essential to ensure their continued performance and safety.